So in this video, we are going to be covering how to approach and solve the subset problem from homework 3. So let's take a look at the problem right now first. So we have given a list of unsorted integers and another integer k. Determine if you can sum an arbitrary number of the elements of the list and get the exact value. No, we're only trying to get here whether it is possible to create the sum. We're not asking you to return which elements are necessary, but simply, is it possible? So let's look at some examples here. We have this first list here, which consists of only positive numbers, and we can clearly see that it is possible to construct the number 24 from this list. We have the second list here, once again, just 3 simple numbers, and none of these numbers are going to give you 10. And then we have a third example here, where we have a negative number. So if we sum 2 of the positive numbers and then the negative number, we get the solution again. So what you normally want to do when approaching a problem like this is give it like 5 or 10 minutes of thought originally, and see if you can come up with a solution. If you can't, you should never be afraid to Google stuff, because if when you're at your job, your boss is going to be like, no, you can't use Google. Your boss is going to be like, okay, why did you spend so long on this if there is a simpler solution that you could have found on Google? And if you just Google this problem, you would have found a Wikipedia article which basically details an in-depth algorithm on how to approach this problem in several different ways. You could have also used LeetCode and many of the other sites, which will not only just give you the code that you need for the problem, but will also provide you with an in-depth explanation on how to solve the problem. So you won't be like, oh, I'm just copying the code from this place. No, but that's not going to be the case, because you're going to take the time, if you read through the article, to learn how the problem works. So you should never be afraid to Google something if you don't understand it. So now back to the problem. So it is clear, once you give it some thought, you might think, okay, so there's no way I can really get this done in an efficient manner, because you're probably thinking, I have to test out every single combination of these sets to see if one of their sums will give me the answer. So some of you, I understand, use iter-tools, but that really actually detracts from the learning experience for this problem, because iter-tools will create all the combinations for you, and that really removes a lot of the thinking, since all you would have to do then is loop through all the different combinations that iter-tools will provide you, which is not necessarily going to be very beneficial to you. Now, when you're looking at this problem, it is good to try to think about exactly what you're trying to do. So given an array, like this first one here, when you're looking at every single item, you're trying to make a binary decision at this point. You're trying to decide, do I want to have this item in my solution set, or do I not want to have this item in my solution set? And because you're going to have to make n of those decisions, because you want to decide, do I want to have 1 in my decision set, true or false? Do I want to have 5 in my decision set? In my ultimate set. You have to make the decision, true or false. And then you're going to have to make n of those decisions in a row, and there's two possible options here. The runtime of this problem, while you guys don't truly understand it yet, is going to be on the factor of 2 to the n, because I have I have a binary decision, which is 2 options, true or false, and I have to make n of them for every time, because of all the numbers I have to decide. So I have that many possible sets I can create from this, because whether I want to include 1 in the set, whether I want to include 5 in the set, whether I want to include 4 in the set, and I have to decide whether I want to include it or not. So looking at that number, as you saw, it's not so much even runtime, it's just 2 to the n is the number of possible sets you can create with this many elements, because n being the length of the set, or length of the array. So here, some of you might jump to thinking, if you have learned it, you might be like, oh, I can use recursion. And at this point, I'm just going to explain a simple recursive algorithm that might solve it, and I'll also explain some of the drawbacks. And if you don't know recursion yet, that's fine, because the solution I'll be detailing later does not necessarily require recursion. So I have this array, right? So I can say, if the length of my array is 0, I just want to return false, because this means that there's nothing left in my array at this point. So this is my base case. There's nothing left in my array, so there's no way the items in my array can possibly get me to the value I'm looking for. So I'm just not going to return false here. Okay. So then I have my else statement. So now I want to see if the element that I'm looking at, so because what I'm going to be doing in this recursive algorithm here is I'm going to given this array, right? So 1, 2, 3, 4, 5, 6, 7. I'm going to go through each element and see whether I want to include it in my array or not, in my ultimate solution. So at each recursive step, I'm going to look at this first element, and I'm going to take its value and see, okay, does this help me towards my goal? So if this first element here, which is array sub 0, is the value, I can return true, because I'm basically done in this case. Now, my other case, I want to see whether this element in conjunction with all of the rest of the elements in the array can possibly give me my answer. So I'm going to return true. I'm going to return subset sum. And then here, I want to look at the rest of my array. So I want to have 1 colon, which will just give me the rest of my array. And then the value minus the array sub 0. So what this will effectively do is this will run subset sum once again on the rest of my array and just see if this value can contribute to the value of the towards the total goal. So this just sees if I can use this element in my solution, or I want to see if it doesn't contribute. So I can do subset sum array 1 colon. And if you don't really care about the recursive solution, you can just skip ahead in the video. I'll include a timestamp. So here, I have this now. Because now I have 2 options. I can either include the element in my solution, or I can not include the element in my solution or in my solution subset. And I just keep on moving down the array, and I keep on shrinking the array each time. So that's how I'll eventually reach my base case of length equal to 0. Because I'll just keep on shrinking the array each time, and I make a binary decision: do I want to include this element or do I not want to include this element? And if I eventually find that the element, I've reached my goal, that's perfect, we're done. Otherwise, I'm just going to keep on recursing down. Now, there is a major flaw in this problem, in that Python, for recursion in particular, it only lets you do a certain number of recursive calls. So for an extremely large array, and because I said there are 2 to the n possible subsets, for an array of length n, we have a lot of different subsets. So it's going to be very problematic for larger inputs. And I have a test case file here where I designed some simple tests. I have some small arrays here, and I have some much larger arrays here. And I'm just testing to see if these will pass. So if I go into my terminal here, and I try to run this Python file, okay, it ran in a decent amount of time. That's fine. Okay. But I want to try something different now. So this recursive solution is fine for right now, but I think there is a better one that you guys, most of you should be able to get to, hopefully. I need to delete all of that. Okay, so should be over here. Okay. So now what I want to do is I want to try to do something very similar to that. So I'm going to first do a check here if the length of my array is 0. This is just checking an edge case here, so I want to return false because I'm not going to be able to do anything with this. So then I want to create a very simple algorithm. So I'm going to have a list of sums. I'm going to create another list of sums. Okay. So to this, we can append our value first. So I'm going to do something very similar to what I did before, where I'm going to look at each value and I'm going to see whether it's going to help me towards my sum. So here, I'm going to append to this a tuple, and the tuple is going to be of this form right now. I'm going to append, this is the value I'm going to append to it. I'm going to append an array index, and the goal of what I want to see from the rest of the array after this, for this index and everything following this index. So right now I am at index 0, obviously, and then the goal we want to achieve is value. So we have appended it to that. Now I'm going to create a while loop here, which is similar to a for loop, except it's just going to run, and I'm going to have this continue to run while the list of sums is greater than 0. Fair? Okay. So now what I want to do is I want to get an item from list of sums. So I'm going to do index index and goal value. And I'm going to ask list of sums. I'm going to call the pop method, and the pop method will just give me the last element that I added to it. So it doesn't really matter at this point how I choose to organize it. I just want an element from it. So now I want to do two crucial checks. I want to check if my index is greater or is equal, check greater than or equal to the length of my list of sums. Or sorry, check if it's greater than or equal to my array. And what this means is that now I've reached an index that's past my array, so I've gone past the end of the array, and if I have, I just want to continue because I no longer want to look. I no longer want to add items based on this index because I've already exceeded where I want to go. Now, once I do that check, I can see if my array subindex, my array of subindex is going to be equal to my goal value. And if it is, this is the obvious case we have true now because we have found a subset that is going to be equal to the goal value. So now's the other step that we have. So we need to continue to add elements to our list of sums. So I'm going to have list of sums here. Computer decides to work. And I'm going to append to it 2 items. And now this is very similar to the recursive solution that we had here. The first tuple I want to append to it is the index plus 1. So this means look at the next index now, and I want to just keep the goal value as it is. Now we have another list of sums, append, once again, index plus 1, and now I want to do the goal value, and I want to append to it, and I want to subtract from this now, array sub 0, array sub index. So in this case now, I have used the array sub index value in my solution, and now I want to just append to my my little list here, so I can just keep on adding elements to my list, and then every time I'm just going to keep on moving the index pointer 1 over until I eventually get to an index that's going to be greater than the length of my list, or I reach a point where I found an item that is equal to my goal value. So once I reach either of those states, I can just keep on going, and I'm just going to keep on going until I've exhausted all possible subsets now. So if I have exhausted all possible subsets, I'm going to return false, because that means I wasn't able to find it. So the important thing are these 2 lines here now. So this is not using recursion, this is just using one while loop, and now I'm just going to keep on moving the index over every time, and I'm going to just do a binary decision at this point. Once again, I want to see if I want to include this index element in my goal, towards reaching my goal, or I want to just not include it. So I'm going to add 2 items to my list every time, and I'm just going to keep on looking at it like that. So now if I try to run this script here, I'm going to get, it passes those base tests very fast, but it takes a really long time on the rest of the stress tests. So this is there's probably something we can do to improve this at this point. So now if I look at something very similar, right? If I have an array of 1, 2, 3, 4, 5, 6, 3, 4, 5, negative 10, 30, right? So I have here, and if I ask you to give me something, give me a subset that's going to equal negative 30, you're going to obviously be able to, just looking at this, tell me that this is totally not possible, because the sum of all the negative numbers here, if I just make this a negative factor, I guess, the sum of all the negative numbers here, well, just that sum in general will not give me negative 30. And I look at all the positive numbers I have as well, and I will also see, once again, there's no way for me to get to that value. So we can do some pruning here and eliminate some of the items that we could possibly add to our list here. So our possible list of solutions. So we can create a positive sum. We can have pos sum, and I'm just going to do a sum function here. And I want to sum value item for item in array if item greater than or equal to 0. Okay. And I want to have a negative sum. Sorry. Okay. So now I have a positive sum and a negative sum, right? And I figure might as well just keep on, like, I don't want to just care about the positive sum and the negative sum for the whole array. Every time I look at an index, I want to see if the positive sum and the negative sum of everything after that index is going to be in the array. So, right? So I don't want to look at the full array at this point. Every time I'm looking at this list here, I want to see if everything after this item has a positive sum or a negative sum that is greater than or less than, I guess, if it's negative here, this goal value. And I'm changing the goal value each time. And if it is the case, that means I'm never going to be able to get to that goal in general, and I can just stop adding elements based on this item. So I have a positive sum and a negative sum here. So I'm going to go ahead and append that to this tuple, because a tuple can just be as many things as I want. Pos sum, neg sum. Okay, so I have a positive sum and a negative sum. So I can just get those values here too. Pos sum, neg sum. So I have the positive sum and the negative sum. So I have this decision here once again. Now, I can make another quick decision here. If the goal value is greater than my positive sum, once again, I no longer want to, that means that whatever subsets I'm going to be creating with what I have at this point will no longer, there's no point in continuing to go based upon this index and then these goal values. So I no longer want to add values based upon the index and the goal that we have, because at this point there's going to be nothing that we can do to get the value. So I'm going to just continue, which means that I do not want to go ahead and just find the I no longer want to go ahead and continuing to add elements based upon this. So this basically will circumvent me adding 2 extra elements, and this will also circumvent me from adding too many elements. So if my goal value is now less than the negative sum, that means that there's no possible way for me to get to that goal value, because all the negative values in the future are no good. So I will never be able to get to that value. So once again, this will also prevent me from adding these 2 elements here. So this will shorten the number of elements I'm going to be adding to my list every time. So this is a little bit of pruning here. And then once again, I probably want to update my positive sum and my negative sum. So I'm just going to have a quick if statement here. So if the array subindex greater than or equal to 0, so if it's a positive number or 0, I'm going to just do pos sum minus equals array subindex. So that means I just don't want to include it in my positive sum in the future, else neg sum plus equals next. Okay. So oh wait 1 second. Okay. So effectively what this is doing now is I no longer want to include this value in my positive sum or negative sum, because I want to look at the negative sums and positive sums for everything after this index now in the future, because I just want to keep on shortening that. Because if I'm looking at this element right now, I don't really care what the positive sum of everything before and after it is, because I'm never going to be looking backwards. I'm only going to be looking forwards. So I only really care what the positive and the negative sum of everything after this element is. So I'm going to add here pos sum neg sum. Add here pos sum neg sum. Okay, so I have this, and if I try to run these test cases, and this is still running, which okay, so now I try to run it nice and fast, because I did a lot of pruning now at this point, where I'm able to tell, okay, there's no possible way for me to, if I'm at index 4 right here, if I'm at the third item, or index 3, the 4th item, number 4 here, and I see that everything after me, there's no way for me to get like negative 20 for everything after this. I no longer have to continue adding these items, because the way that this the running time of this really builds up is that I just keep on adding 2 items. For every item I take off, I add 2 new items, which can really be a problem. And if you get a really big data set. So if any time you have an opportunity to just not add these 2 items, just take off an item and not have to add 2 new items, you want to take it. So you can see if the positive sum is not reachable, If the goal value is greater than the positive sum, I'm not reachable. I just don't have to add these two items here. If the negative sum is not reachable, if the goal is beyond the negative sum, it's not reachable. I can once again we can just skip these two statements here. And by doing this, we really get to a point now where it runs relatively fast, but this is still exponential because I still have to, in the general case, for every two items I add, one item to take off, I add two new ones. Now, this is going to be beyond the scope of the course, but you can use dynamic programming, which is basically where you do something similar to this, but you're able to cache different informations to help you expedite the running time, to keep it from being an exponential runtime problem. And by exponential, I mean because, as I said, this is going to be a 2 to the n running time, and that n is an exponent, so we call this exponential runtime. And there is ways to circumvent this using dynamic programming, which, if you really want an in-depth explanation of it, if you look at this Wikipedia article, it does go over polynomial runtime algorithm, which is going to be using dynamic programming. It says right here, but I'm not going to go over it since it is beyond the scope of the course. So hopefully this helped. If it did, let us know on Piazza or Slack, or I guess in the comment section of this video, and we'll continue to do things like this. I hope this helped, and good luck on future homeworks, and try to approach these problems in this way.